Okay, let's take a look at today's lesson. What we're going to be looking at actually is something that's going to be, it's actually relating to what we're getting ready to do. We're getting ready to build a house out of connects. We're getting ready to test the vibrations as like a simulated earthquake. And so that's kind of plays into this particular lesson where we have this formula right here describes this graph. So let's look at the graph. The graph, as you can see, starts out oscillating, and then over time it calms down. It goes to basically no oscillations. And so this is called a damped, D-A-M-P-E-D, damped curve. So what's happening is the exponential, that's the multiplier, is altering the motion, right? It's changing it. It's decreasing it. And so that's kind of the thing that we're going to be looking at. What can we do to decrease the amount of oscillations or movement in a structure to help to be more resistant to earthquakes so they don't just fall apart. All right, so we've got some Greek letters today that I think was kind of freaking some people out, but let's just embrace it. It's okay, right? That's all right. We're going to look at the different ones. We have this equation. You do not have to memorize the equation. That's going to be the equation of the curve that we're going to be looking at. So students are asking, like, what kind of questions are going to be on a quiz? Well, this would be like questions that would be on a quiz. You'd be given a picture like this, and you'd be asked to find the equation. And also, you very well could be asked to tell me what the variable means. What does it mean? So let's look at them. So we have A. That's just a regular A. We kind of like that. That's just amplitude. We have this little thing. Looks like this. That's lambda. Kind of I don't know. It kind of looks like a Y looking little thing. This is lambda. This is beta. And so those are the two Greek letters in this equation. We have a couple more Greek letters down at the bottom that we're going to talk about. In multivariable calculus, we use lots of Greek letters. So this is just, we don't use a whole lot in BC calculus, but we do in multivariable. So these are just things we get used to. So let's look at, we're going to go step by step into finding these. We need to find A, we need to find lambda, we need to find beta. Those are the numbers that we need to find. And this is a definite calculator lesson, so hopefully you have your calculator with you. If you would get that out, that's going to be quite helpful as we go through. We would not do this by hand. All right, so A, the amplitude, the peak amplitude, we're looking for the biggest amplitude, right? This equation can be written either with cosine or with sine. And let me tell you how you can tell. So at time 0, if it starts at a maximum value, we're going to use cosine. That's the one we're going to use. And that makes sense, right? Cosine starts at its max. If at time 0 it starts at 0, we're going to use sine to write our equation. So that's how we tell whether this piece is going to be sine or cosine, is to where we are at t equals 0. In this particular case, at t equals 0, we are at a maximum, so we're going to use cosine. And we can read the amplitude off of the graph. We don't have to do anything fancy to get the amplitude. So in this, let's explain some things. So this is a cosine. This is the easiest type to get the amplitude from, because this equation, this exponential, has not had time to, minimize the curve, the oscillations. So we are going to say that amplitude is going to be 1. We're just going to take it off the graph. So for us, we're going to say A is 1. Now, if this were a sine graph, and you do have one on your daily work that's a sine graph, let's talk about it. The sine graph is going to start here at 0, so we really can't tell amplitude from at t equals 0. We're going to have to go out a little ways. And so what I want you to do is be a little, overestimate A when you're doing a sine graph, because, it's already, the exponential has already started its effect of making it smaller and smaller. So we want the peak amplitude, which is the largest amplitude. And if you have questions, you can ask me on the daily work on the sine one. All right, so we found A. Now we need to find beta. And so we know, this is a formula. So let's talk about formulas. We know from, first semester that the period equals 2 pi over, and they're calling b, the b that we usually call, they're just calling it beta. So what they have done here is they've just solved for beta, that's all. So we solve for beta, and we get that beta is 2 pi over the period. So let's see if we can calculate the period. So what we want to do is on the graph is we want to read from a maximum location to a maximum location. That's what you want to read. And these are all estimates, so all of our graphs equations may be slightly different, and that's okay. So I'm looking here, it looks like we are so close to 1 right here with this second maximum right here that I'm going to just estimate at 1. I mean, I guess you could say 0.9 if you really wanted to, because it's a little bit off, but I'm going to go with a 1. So we're going to say that beta is 2 pi over 1. And again, so let's talk about that. It probably is a 1 because this little exponential is already working its magic, right? It's decreasing, it's shrinking the oscillations, so I'm sure it was originally a 1. So now we have our amplitude and we have our beta. So beta is 2 pi. The last thing that we need to be able to write our formula is lambda, and this is the part where some students were getting really confused with lambda. So let me see if I can be a little bit more specific. So what we want to do to find lambda is we want to find an additional point on the graph. The point that we choose really wants to be, we need it to be beneficial to us, not hard. So I know that I'm going to have to plug a t right here and right here. So it would be really convenient if t was 1. I would really like that, right? We would have a t of 1 here, t of 1 there. If we can use a t of 1, that would be great. In this case, we can. If the t of 1 was on the, if it crossed the x-axis, we couldn't use that t equals 1 because the y value of 0 is not very helpful in our equation. But we're going to use, so what I'm going to do is I'm going to estimate the value at t equals 1. So we're going to use t equals 1, and I estimated the y value to be, let's see, up here would be 0.25, so I estimated that to be 0.2. Now you may have estimated it to be 0.15. That's fine. Okay, we cannot be extremely precise here. This is an estimate. So as long as we're close, it's just fine. So don't stress about the estimate. But that's the estimate that I use. Now what I'm going to do is I'm going to put all of the numbers that I have into here, and I will only have left a lambda to solve for. And so that's what I'm doing. So for my y value, I'm replacing it with 0.2. A we know was 1. Then I have e to the negative lambda, and t is 1. And then I have cosine of beta times 1. Okay. All right, so we have, and beta is 2 pi. Sorry, I got to put that 2 pi in there. We already found beta, so let's fix that. Okay, so we know that that's 2 pi times 1. Okay, so now I'm just going to, I can do this by hand. I don't need a calculator for this part. We know that 2 pi times 1 is 2 pi. We know that cosine of 2 pi is 1. Right, this right here is going to 1. So I basically have 0.2 equals e to the negative lambda. And we just finished a unit where we solved these kinds of things, remember? So how do I solve for lambda? What do? I take the natural log of both sides, right? So I have natural log of 0.2 equals negative lambda. So lambda is negative natural log of 0.2. All right, now I have all of the variables that I need to write my equation. So I have, let's write it up here. So we have x of t equals, we said our a value was 1, e to the, see now the lambda is negative right here, and so is this. This is negative also. So a negative negative gives me a positive in the equation. So it's ln 0.2t, and then our cosine of 2 pi t. And that's our equation. Okay, I'm going to pause there for a second. Is everybody okay with writing the equation? Yes. Right here? That's lambda. Yeah, or you could just think of it as a y. Yeah, that's what we're solving for. We're solving for lambda. Other questions? Are we okay with getting the equation? Okay, so the equation, we're going to take that equation and we're going to use it to find something else. So I need actually to erase. Has everybody got what they need on here? So I need to erase and scroll down. All right, so we've got two variables of interest that we're going to be looking for. And so we have two more Greek letters, yay. Okay, these are the two variables. This one is the Greek letter omega, and this one is the Greek letter rho. So omega and rho. Okay, so I may ask you on a quiz, what is omega? What is it? Well, omega is the angular natural frequency in radians per second. It's the frequency in radians per second. Okay, I may ask you, what is rho? Well, rho is the damping coefficient. Basically, the measure of how oscillations in a system decay. These are the two variables that engineers are very interested in. They're very interested in those variables because they affect the movements. They want to change those variables to make the oscillations less, right? We don't want a lot of oscillating. We don't want the building to be shaking back and forth because things like fall off of it, right? We want it to try to be able to move with the earthquake. So these variables are important. Another variable we're going to look at it as natural frequency. We actually talked about natural frequency yesterday, if you recall. The natural frequency, I gave an example like of a pendulum and a clock. You know, if you hold the pendulum of the clock and you let it go, it's going to do a little bit of crazy stuff, but it's going to eventually calm down and get to its natural frequency. And so the natural frequency is actually measured in hertz. Hertz, this basically what a hertz is it's 1 cycle per second. So hertz is 1 cycle per second. Okay, and that's what our natural frequency is going to be measured in. Okay, so now our task is to find out what those two variables are. What are the numeric values of those variables? In order to do that, we're going to use these two equations. Again, you do not have to memorize these two equations. I would give them to you. But these two equations, we know what beta is already, and we know what lambda is already. Right? We're going to use beta and lambda in these two equations, so we'll have two equations with two unknowns. And we're going to do a system. We're going to use a system to solve. So let's set up the equations. So we knew beta was 2 pi. So 2 pi equals omega times square root of 1 minus rho squared. We also know that lambda, what was that? Negative ln. Lambda was negative ln of 0.2, and that is equal to rho times omega. Okay, so this is a pi. So now our job is to figure out, I'm going to use substitution, and I really don't want to solve for rho. It's just a mess in here. That's a mess. I don't want to mess with that. So what I would do is I would take this equation and solve it for omega and then substitute omega out. So let's do that. Let's solve for rho. So omega is going to be negative natural log of 0.2 divided by rho. And now I'm going to put that in this equation. So I have 2 pi equals rho, which is negative ln 0.2 over rho, times the square root of 1 minus rho squared. This is the equation that I'm going to put in my calculator. And let me give you a chance to copy it down because I need to erase this and go to the calculator. I'm going to work through it with the calculator with you. Because it looks a little weird, I just want to make sure we're okay. So that's the equation I'm going to use. Does everybody have that? Are we ready? Okay, so let me erase this and let's go to the calculator. Okay, so on our calculator, I would go to y equals, And the way I solve is I put the left side in one side and the right side in the other. So this would be 2 pi. And then the left side we had, what do we have? We had negative, so I want a fraction alpha y equals inner. So we had negative natural log of 0.2. Right, negative natural log of 0.2 over rho, we're just going to use x, times, and then it was the square root of, so square root of, what was it? It was 1 minus rho squared, so 1 minus x squared. Okay, I'm going to look at my window. So I don't need many negative x's at all. I don't even probably need that many. Maybe negative 2, 5 max for x is fine. I don't need many negative y's, and let's see, we're intersecting it with 2 pi. We know 2 pi is like 6 point something, so we know 8 should be pretty good. So let's just graph it and see how weird see how weird this graph looks, this part. They all look like that. And if your calculator is not zoomed in very well, it's going to appear that these don't even intersect. But they do. They're going to. It may be a really small number, but they're going to. You just might need to focus it, to zoom in more with your calculator. So let's find it. So we would do second trace. We're going to do our intersection. And so let's scroll over there. And so we do enter, enter, and then enter. So this is our intersection. This is what rho is. Rho is going to be 0.248, blah, blah, blah. Okay, we can certainly round it on our paper, but as we need to find omega also, we should not round it for that. Okay, we need to keep all the numbers. So what I would do, so that's going to be rho. I'm going to go to a clear screen, so second quit, and I'm going to hit X, enter, so that I get that solution here on my clear screen so I can work with it. Okay, so this we said was rho. And if we look back on our work, on the little equation that we solved, we had, what did we have? We had that omega was, what was it? Negative natural log of 0.2, negative natural log of 0.2 over rho. Okay, so to find omega, I'm going to need to do this negative natural log of 0.2 over this whole thing right here so that we don't have any issues with rounding. So we have negative natural log of 0.2, and that is going to be divided by this right here that I'm going to grab and bring down there. Okay, so omega is the 6.486. Okay, so we have both of those two variables that we were looking for that are significant for us. Okay, so is everybody good with that so far? We have just one more thing to do. Let me go back to the worksheet. Okay, so the last thing they want us to do is find the natural frequency in hertz. Okay, so that formula is given to us right here. The natural frequency is omega over 2 pi. So we have omega, we just calculated it. So 6.486. Of course, we're going to use all of the numbers in our calculation. We just round for our answer. 0.3946 all over 2 pi. And that's going to give us a natural frequency of 1.032 hertz. All right, and that is the lesson. How are we with that? I know it's kind of intense, right? There's a lot going on, a lot of Greek letters, but are there any questions? Yes? That one, it's just the beta. Let's go back up here. It gives us the little definition right here. So beta is our what was on the yesterday's stuff. It's basically related to the period and to how many times it oscillates. Yes. Yeah, I would give you, on a quiz, I'm going to give you these 3 equations. And, you know, if I want you to find frequency, I would give you that equation too. The one that we just found, that one at the bottom. Yeah, you don't have to memorize these equations. Okay? Well, beta, yeah, you should know that already, right? Because that's period equals 2 pi over b. We already know that. Right, so you should know that. I won't give you that one. Okay? Are we good?